Deep learning is a subset of machine learning in artificial intelligence that imitates the workings of the human brain in processing data and creating patterns for decision-making. This field has gained immense popularity due to its ability to handle large amounts of unstructured data and derive meaningful insights. It is inspired by the neural networks in the human brain, which consist of neurons that communicate with each other. Deep learning models are designed to perform tasks such as recognizing speech, identifying images, and making predictions. These models learn from vast amounts of data, allowing them to improve their performance over time. In essence, deep learning enables machines to learn from experience and make decisions similar to humans. This capability sets it apart from traditional machine learning techniques. In the broader context of AI, deep learning plays a crucial role. While AI encompasses the general concept of machines being able to carry out tasks in a way that we would consider smart, deep learning provides the technical backbone that powers many of these advanced applications. As we continue to generate and collect more data, the importance of deep learning and extracting value from this data becomes increasingly significant. Neural networks are the foundation of deep learning. They consist of nodes, or neurons, that are organized into layers. There are three main types of layers in a neural network: input, hidden, and output layers. The input layer receives the initial data, the hidden layers process this data through weighted connections, and the output layer produces the final result or prediction. Activation functions play a vital role in neural networks. They determine whether a neuron should be activated or not, introducing nonlinearity into the model. Common activation functions include the sigmoid function, which squashes input values between 0 and 1, and the ReLU, rectified linear unit function, which outputs 0 for negative inputs and the input itself for positive inputs. These functions help the network learn complex patterns in the data. Loss functions measure how well the neural network's predictions match the actual outcomes. They provide a way to quantify the error in the model's predictions. For instance, the mean squared error is commonly used for regression tasks, while cross-entropy loss is used for classification tasks. By minimizing the loss function, we can improve the model's performance. Understanding these key concepts is essential for grasping how deep learning models work. The interplay between layers, activation functions, and loss functions enables neural networks to learn from data and make accurate predictions. Feed-forward neural networks are the simplest type of neural networks. In an FNN, information moves in one direction, from the input layer through the hidden layers to the output layer. There are no cycles or loops in the network. FNNs are used for tasks like image recognition and simple classification problems. Convolutional neural networks are designed for processing structured grid data, such as images. They use convolutional layers to scan the input data with filters, capturing spatial hierarchies and patterns. CNNs are widely used in computer vision tasks like object detection, image segmentation, and facial recognition. Their ability to automatically and adaptively learn spatial hierarchies of features makes them highly effective for image-related tasks. Recurrent neural networks are designed for sequential data, such as time series or natural language. They have connections that form directed cycles, allowing information to persist. This makes them suitable for tasks like language modeling, machine translation, and speech recognition. RNNs can remember previous inputs due to their internal state, which helps in modeling temporal dynamics. Generative adversarial networks consist of two neural networks, a generator and a discriminator. The generator creates fake data, while the discriminator evaluates its authenticity. These networks are trained together in a zero-sum game, where the generator aims to produce data indistinguishable from real data, and the discriminator aims to distinguish between real and fake data. GANs are used for generating realistic images, video game content, and even music. Training a neural network involves two main processes: forward propagation and backward propagation. In forward propagation, the input data passes through the network, layer by layer, until it reaches the output layer. The network's prediction is then compared to the actual target using a loss function to calculate the error. Backward propagation, or backpropagation, is used to minimize this error. It involves computing the gradient of the loss function with respect to each weight in the network and updating the weights to reduce the error. This process is repeated iteratively, allowing the network to learn from the data. The gradients are calculated using the chain rule of calculus, and the weights are adjusted in the direction that reduces the loss. Optimization algorithms play a crucial role in the training process. Stochastic gradient descent is a popular optimization algorithm that updates the weights using small, random batches of data rather than the entire dataset. This makes the training process faster and helps avoid local minima. The atom optimizer is another widely used algorithm that combines the advantages of both SGD and RMS prop, adjusting the learning rate for each parameter. Effective training of neural networks requires careful consideration of these processes and algorithms. Properly tuned, they enable the model to learn from data efficiently and achieve high performance. Section 5. Hyperparameter tuning techniques. Hyperparameters are the settings that govern the training process of a neural network, but are not learned from the data. Examples include the learning rate, batch size, number of epochs, and the architecture of the network. Properly tuning these hyperparameters is crucial for achieving optimal performance. Grid search is one common technique for hyperparameter tuning. It involves exhaustively searching through a manually specified subset of the hyperparameter space. While effective, grid search can be computationally expensive, especially for large models with many hyperparameters. Random search is another technique that samples hyperparameters randomly from a distribution. This method can be more efficient than grid search, as it does not evaluate every possible combination, but rather explores the hyperparameter space more broadly. Bayesian optimization is a more advanced technique that uses probabilistic models to find the optimal hyperparameters. It builds a surrogate model of the objective function and uses it to make decisions about which hyperparameters to evaluate next. This method is more efficient and can lead to better performance. Effective hyperparameter tuning can significantly improve the performance of a neural network. By carefully selecting the right values, we can enhance the model's ability to learn from data and generalize to new, unseen examples. Section 6. Evaluation metrics for classification and regression. Evaluation metrics are essential for assessing the performance of neural networks. For classification tasks, common metrics include accuracy, precision, recall, and F1 score. Accuracy measures the proportion of correctly classified instances out of the total instances. Precision is the ratio of true positive predictions to the total positive predictions, while recall is the ratio of true positive predictions to the actual positive instances. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances both. For regression tasks, metrics like mean squared error, mean absolute error, and R-squared are commonly used. Mean squared error measures the average squared difference between the predicted and actual values, while mean absolute error measures the average absolute difference. R-squared indicates how well the predictions approximate the actual data points, with values closer to 1 indicating better performance. Confusion matrices are also useful for evaluating classification models. They provide a detailed breakdown of the model's performance by showing the counts of true positives, true negatives, false positives, and false negatives. This allows for a more granular analysis of the model's strengths and weaknesses. Choosing the right evaluation metrics is crucial for understanding the performance of neural networks. These metrics provide valuable insights into how well the model is performing and where improvements can be made. Section 7. Real-world applications. Deep learning has a wide range of applications across various fields. In computer vision, it is used for tasks like object detection, image segmentation, and facial recognition. Self-driving cars, for instance, rely on deep learning models to interpret visual data from their surroundings and make driving decisions. In natural language processing, deep learning is used for language translation, sentiment analysis, and text generation. Virtual assistants like Siri and Alexa use deep learning to understand and respond to user queries. Speech recognition systems also leverage deep learning to convert spoken language into text. Healthcare is another field where deep learning has made significant strides. It is used for diagnosing diseases from medical images, predicting patient outcomes, and personalizing treatment plans. For example, deep learning models can analyze X-rays and MRI scans to detect anomalies with high accuracy, aiding radiologists in their diagnoses. These applications demonstrate the transformative potential of deep learning. By harnessing the power of neural networks, we can develop systems that perform tasks with a high degree of accuracy and efficiency, improving various aspects of our daily lives. Section 8. Deep Learning Tools, Frameworks, and Hardware. Several tools and frameworks have been developed to facilitate deep learning research and application. TensorFlow and PyTorch are two of the most widely used frameworks. TensorFlow, developed by Google, provides a flexible platform for building and deploying deep learning models. PyTorch, developed by Facebook, is known for its dynamic computation graph, making it easier to debug and experiment with models. Hardware also plays a crucial role in deep learning. Graphics processing units, or GPUs, are essential for training large models, as they can perform parallel computations much faster than traditional CPUs. NVIDIA's CUDA platform has become the standard for GPU-accelerated deep learning. Other tools like Keras, a high-level API for building neural networks, and MXNet, an efficient deep learning framework, are also popular among researchers and practitioners. These tools provide a range of functionalities, from model building and training to deployment and optimization. The combination of powerful tools, frameworks, and hardware has accelerated the development of deep learning solutions. These resources enable researchers and developers to build complex models efficiently and effectively, pushing the boundaries of what is possible with AI. Section 9. Challenges in deep learning. Despite its successes, deep learning faces several challenges. One major challenge is the need for large amounts of labeled data. Training deep learning models requires vast datasets, which can be difficult and expensive to obtain. Data augmentation and transfer learning are techniques used to mitigate this issue, but they do not eliminate the need for substantial data. Computational cost is another significant challenge. Training large models requires extensive computational resources, which can be prohibitive for many organizations. Cloud-based services and specialized hardware like TPUs or tensor processing units are being developed to address this issue, but the cost remains a barrier for widespread adoption. Interpretability is also a concern. Deep learning models are often considered black boxes because it is difficult to understand how they make decisions. This lack of transparency can be problematic, especially in critical applications like healthcare and finance. Efforts are being made to develop methods for interpreting and explaining model predictions, but this remains an active area of research. Bias in deep learning models is another critical issue. Models can inherit biases present in the training data, leading to unfair or discriminatory outcomes. Addressing bias requires careful data curation and the development of techniques to detect and mitigate bias in models. Section 10. Future Trends in Deep Learning. Looking ahead, several trends are shaping the future of deep learning. Self-supervised learning is gaining traction as a way to reduce the reliance on labeled data. This approach involves training models to predict part of the data from the rest of the data, enabling them to learn useful representations from large amounts of unlabeled data. Federated learning is another emerging trend. It involves training models across multiple decentralized devices or servers while keeping the data localized. This approach enhances privacy and security, as the data does not need to be centralized. It has potential applications in healthcare and finance, where data privacy is paramount. Neural Architecture Search, or NAS, is an automated approach to designing neural network architectures. NAS algorithms explore the space of possible architectures to find the best performing model, reducing the need for manual design and experimentation. Explainable AI, or XAI, is also becoming increasingly important. As deep learning models are deployed in critical applications, the need for transparency and interpretability is growing. XAI techniques aim to make model predictions understandable to humans, enhancing trust and accountability. These trends indicate that deep learning will continue to evolve and address current limitations. By adopting these new approaches, we can unlock even greater potential for AI and its applications in various fields.